Hello, Pamela. You're mute.
Hello.
Sorry, I know I don't unhide you the way you're expecting to be unhidden.
Yeah,
I
yeah, yeah. I'll just call
I
you lazy.
yeah, no, not lazy. Distrustful of technology. There's a big difference. So I found the control room software in Hangouts is really janky, and I can never seem to make it work right. So um, I trust how the Hangout toolbox works. So, or how the default mute. Anyway, I'm sure this is super fascinating for everyone watching the show. So glad you watched us argue about technology. Hey everyone, I'm Fraser Cain, publisher of Universe Today. That's Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville, and the director of CosmoQuest. And you are watching a live recording of Astronomy Cast, a little old show that we've been doing for 365 episodes.
We have now created an entire year of content. That's a little bit daunting.
Yeah. If you want to just listen to one episode of Astronomy Cast every day, you can do so. Plus, there's all the extra question shows and things like that. So, holy cow. We yeah. We make a lot of content. So, there's that. We never, ever get the email, when you guys are going to make more shows. I've been, I wish I'd caught up, and now I wish you guys could do more recordings. We used to get that we had like 20 shows in the can, and people would listen to all 20, and then they were like, we need more shows. How do you like your shows now? You get lots. All you need. Cool. So you were sick last week. You feeling better?
Mostly.
Mostly
Working
better?
on it.
All right. Well, good enough to record anyway.
Yes.
So you're a total trooper. Well, let's get rolling. Hey, and anyone? You know what? Before we do, just a reminder to everybody that you can use the Q&A app. So if you're watching this video, you can click here to join the conversation, and you can add your questions, and then we will I will try to either incorporate them into the show, or I will we'll answer them afterwards. So I'm going to say hi to, let's see, Nancy Graziano, of course, Jim Meeker, Seb Dustbunny, Guido Bibra, Tony Lynch, Thomas Traniker, Will Adoni, and Peter Waldman, and Michael Jobin. So, hi, everybody.
And I hope we're amusing all of you who are getting snowed on somewhere.
Yeah, it's this is going to be a thing. This is the poor East Coast of the United States is going to be getting the worst storm on record.
New York City, I believe that for Boston, I'm pretty sure Boston's seen worse.
Didn't they just get a hurricane that flooded a huge chunk of the city? I know, but still, like that was a bad
frozen
storm.
Water instead of liquid water.
Yeah, how do you like
totally different phase.
How do you like your climate change now?
It doesn't work that way, and you know
I didn't like it before, and I don't like it now. No, I mean, right, that you can't tie any specific weather event, to a to climate change, but the climate change predicts that there will be more extreme weather. So
yeah,
is this caused by climate change? Maybe, maybe not. Okay, well let's get cracking. Are you ready to record?
I am. I wish it would snow here. It's not. It's very sad.
You wish you would get 3 feet of snow?
I've lived through. I'm a New Englander, but New Englander raised, and I miss snow. And we got a dusting, and you can't make a fallen over snowman that appears to be swimming through the yard with sharks chasing after it. Or take the icicles off the edge of your roof and use them to make like a dinosaur mouth with fangs. There's so much awesome terrorizing yard art you can do to horrify the UPS man, and we can't do it without snow.
We get the perfect snow on the West Coast for that. It's like you can just it's so wet, and so you can just grab a handful and you've made a snowball, and it holds like rock. So it's the best stuff to do. I've made igloos, all kinds of crazy stuff with it. It's great. Okay.
Okay, I'm gonna press record.
Yeah, can we record a show?
Yeah. Okay, I pressed record. It's
right.
Recording. It's recording with the correct microphone in mono. Hi, Preston.
Mine is doing the same. So, all right. Better. setup. Hello, Preston. Oh, no, I screwed it up.
Oh, noes.
Okay. Oh, noes. Okay, I'm good. All right. All right, here we go. Astronomy Cast, episode 365, Gaia. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we'll help you understand not only what we know, but how we know what we know. My name is Fraser Cain. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville, and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you?
Doing great, and just wanted to let people know we get a lot of questions. I don't know, we get a lot of questions sent to me specifically, a lot of questions sent to you, I know specifically, and then we get questions sent to Astronomy Cast, and then we get questions everywhere else. And I just wanted to encourage people, like it's too many for us to answer. Like, I don't know about you, too many. We try by email and stuff, but the best way to send us a question is actually to queue your question up for the show. And the way to do that is you go to the Astronomy Cast page on Google Plus, and you'll see what the next show is. And we always queue up the shows a week in advance. You can go on that, and you can click on the Q&A app, which is available a week in advance, or on the actual just event page itself, and just post your question there. And then we actually set aside half an hour of every single show that we record where we just answer questions from the public. And that is the absolute best way. And so we will look through this, and so we often run out of questions. It's very ironic. We run out of questions for the live show, but yet we have tons and tons of questions that come in by email that we just don't have time to deal with. So that is the best way to kind of get our attention and get in front of us, and when we're in a question answering kind of mood. So if you are interested in that, just when you want to ask us a question, go to the Astronomy Cast page on Google Plus, see the next show, put your question into the event page. I promise you I'll be watching it every week. So, do you agree, Pamela?
Yes, I do.
All right. And also, I also highly recommend that you go to the CosmoQuest community. And so there's a great forum there. Lots of people who will answer your questions about space and astronomy. Some of the best people we know.
Yeah.
All right, let's get cracking with this episode of the show. So the European Gaia spacecraft launched about a year ago with the ambitious goal of mapping 1 billion stars in the Milky Way. Let me do that again. It's going to be happening. Little froggy throat. The European Gaia spacecraft launched about a year ago with the ambitious goal of mapping 1 billion stars in the Milky Way. That's 1% of all the stars in our entire galaxy, which will monitor about 70 times over its 5-year mission. If all goes well, we'll learn an enormous amount about the structure, movements, and evolution of the stars in our galaxy. It'll even find some quasars and maybe planets. All right, this is actually, I think, one of the most exciting spacecraft that's been launched fairly recently. 1% of all the stars in our galaxy. We will have an accurate map of an enormous amount of this. So let's talk about the Gaia mission.
So this is, in many ways, a follow-on to a mission we discussed way back in, I think, the first year that we did this show, and that was the Parkus Mission. And with Parkus, they put out a catalog of nearly 1 million stars out to a distance of 200 parsecs, so about roughly 600 light years. And the goal of that mission was to accurately use the Parallax Method to get both brightness measurements and distance measurements, which allowed us to calculate the luminosity of these different stars and thus be able to more effectively use things like pulsating variables, the Cepheids, to measure distances even further out in the universe. But what we realized is, first of all, there weren't any Cepheids close enough to get the high accuracy that we wanted, which was highly frustrating. And second of all, there were a whole lot of questions that we still couldn't answer with that small of a sphere around the Earth, just 200 parsecs. With this mission, Gaia is going to have 1% accuracy for 700,000 stars out to a few hundred parsecs. So that's big. Then another 20 million stars out to a few kiloparsecs. Then at distances greater than that, out to about 10 kiloparsecs, they're still going to have 10% accuracy. So That's pretty amazing. And then on top of it, this is the mission that just keeps giving. They're also doing basic spectral work, so we're going to be able to get at the surface gravity, the chemical composition, and a myriad of other details of all of the roughly 1 billion stars that this telescope's going to look at roughly 70 times each over the course of its existence.
And in addition to looking at the stars, it's going to be looking at quasi-stellar objects. It's going to be looking at quasars. It's going to find 500,000 quasars.
And it's going to look at near-Earth objects that go through its field, far-Earth objects. Basically, if it's brighter than the 20th magnitude, which is about as faint as you want to go with a 1-meter telescope to get good resolution, if it's brighter than 20th magnitude, it will see it. So we're going to be getting bazillion stars, billion stars, quasars, asteroids, everything else that goes through its field of view.
So let's talk a bit about, now you mentioned the Parkus and the Parallax Method. So do you want to give a little bit more information about exactly how it's going to be doing its science?
So this is where we ask all of you to do a simple yet humiliating science demonstration. Hold up your thumb. Close one eye. Move your thumb so it's blocking some fairly nearby object, and compare the location of the nearby object, in my case the webcam, and some faraway object. Now switch eyes, and you'll see that your thumb relative to that nearby object bounces around. And depending on how near that object is, it will bounce even more relative to further away objects. With cartoons, if you've ever noticed, the way they fake motion is they'll have multiple layers that move across the screen at multiple rates, faking the distance of nearby shrubs, further away trees, much further away mountains. This is because objects that are nearby, compared to our two eyes, appear to jump more, whereas things that are further away require a great deal more motion before they appear to move. Quasars, they just don't appear to move. They're too far away. Now, we know the distance between our eyes, or at least we can figure it out using a mirror and a ruler. We can measure the distance to our thumb. If we wanted to, we could use all of this and the angular jump to start to calculate with basic trigonometry how far away things are.
So I could do that, and I could actually figure out how far away a tree is, or how far away that car is.
Exactly.
Just by measuring the angles of my eyes, my thumb, the angle to the car, and how things change.
And usually people start using different instruments to do this more accurately, but it's not hard calculations. And with the planet Earth, it's not like we can look at a star, close our left eye, close our right eye, and see the star jump. But what we can do is wait 12 months for the planet Earth to go from one extreme side of the sun over to the other extreme side of the sun.
I guess 6 months.
Yes, 6 months. 12 months gets you all the way back to the beginning, doesn't it?
Yes, yes.
So you wait 6 months to get to the other side of the sun, and make your measurements, and nearby stars will appear to jump compared to background galaxies, and quasars are about as background as the galaxy can get.
And so you make this one precise measurement of the position of the star compared to a background object. 6 months later, you make another precise measurement of the position of the star compared to a background object, and you then that gives you some position, some angles, and then break out your trigonometry, calculate. That tells you how far away it is, and even potentially if it's moving, speed.
Now, no, see, there you start to need 3 measurements. So the problem is, if you only make 2 measurements, you don't know how much of the motion is due to the sucker chugging along in its orbit, and how much of the motion is due strictly to its nearby, therefore it appeared to jump. Now, admittedly, unless you're very unlucky, the direction that it's chugging through the sky and the direction that it appears to jump due to the Earth's motion aren't going to be exactly lined up, but you are going to get unlucky now and then. So what you actually want to do is start taking multiple measurements. You measure it over multiple years, and you can see December to December here, the 12 months comes into play. Oh, it moved that far. That means the star has an actual motion in the plane of the sky of however many fractions of an arcsecond per year. Then, due to its distance, it appears to jump with that 6 month. Now, at the same time, there's one more motion that you have to get at, and that's the motion along our line of sight. So it could be moving towards us, it could be moving away from us. We can get at that information using the Doppler shift. And this telescope, calling it a telescope is really an understatement. Gaia is the optical bench that tried to take over science, as near as I can tell. It has more CCDs on it than you can shake a stick at. It has multiple mirrors, multiple systems, and this amazing design that has the light coming on, getting mapped out by one instrument, and then sliding across the field and getting imaged and spectrally analyzed as it goes.
Yeah, I mean, to think about how they're going to be imaging 1 billion stars 70 times. So that means that they're just going to take an enormous amount of data nonstop. That they don't just stare at one star at a time. They have to stare at a whole pile of stars all at the same time in different fields and then move on to the next one, right?
Well, and the awesome thing is the way they're doing it, it's not so much that they move on to the next one as they're constantly moving. The way this system is designed is it has a pair of mirrors that are looking at two different sections of the sky, and the mission, the spacecraft, is sitting out at roughly, it's orbiting around the L2 Lagrange point. This is the same place that we're going to put the James Webb Space Telescope if we're lucky. And while it's sitting out there in its position, it's slowly drifting across the sky with a bit of precession in that. And the angles work out just right that as it drifts across the sky, stars that it's detecting will move exactly along the CCD such that they track down the columns as the CCD reads out. So the CCD is reading out the data at the same rate as the stars going along. It moves all the way across one field, gets detected by the readout instrumentation, moves into the next set, and the way it's set up is it starts out going across, drift scanning across the SkyMapper CCDs, and these are CCDs that basically go light, no light, okay, I've got something, and they decide if there's a star that the rest of the sensors need to look at, and they decide how much of the chips need to get read out in order to make the needed measurements of those stars. Once something has been detected by the SkyMapper, it moves on to the astrometric CCD. These CCDs very precisely measure the centroids of the stars. This is what gets used to make the parallax measurements, gets used to look at all of the different things that can happen down to the level of super Jupiters tugging the stars around, creating slight deviations over time. Once they're done with the astrometric CCDs, then they get passed on to two different spectral analyzers, one that looks at the blue, one that looks at the red. This is to get at the temperature and the composition. And then finally they get passed off to some radial velocity CCDs that look strictly at the calcium H and K lines and very, very precisely measure how fast is that star moving towards us or away from us.
So I think knowing the position is important, and then knowing the movement, I guess in 3 dimensions, we're going to know how far it's moving side to side and how far it's moving forward and back, and that will tell us really where that star is moving in comparison to us in the Milky Way. And so you can imagine them putting together this simulation of all the stars and mapping it forward and backwards and knowing where all these stars are going and how they're interacting, and it's mind-bending. So you talked briefly about being able to tell a bit about sort of like what the stars are made out of, right?
Right. So when we're trying to figure out a star's composition, what we look at is the bright and dark patches, stripy bits in this case, that appear in a dispersion of the light. So you take the light from a star, in this case you put it through a prism, And instead of seeing a point, what you see is a streak. And within that rainbow of light, there'll be places that are darker. This is where gases inside the star's atmosphere are pulling the light out, and instead of letting the light continue on its merry way to be observed, are taking that light, absorbing it in as part of a transition. Now, in other places, you might see a place where that rainbow is super bright. This is an emission line. It's someplace where the atoms in the star are radiating light in a specific transition as the electrons jump to a lower energy level. By measuring this fingerprint of bright and dark lines, mostly dark lines, we're able to get at how much of the different elements are in the atmosphere of the star. The depths of the lines change with temperature, with amount of composition, so you have to look at a lot of different things. But what's kind of awesome is the spectra gets you at what it's made of, what the surface gravity is by how much those lines get broadened out, once you take into account the fact that this star is rotating. So you now have how fast it's rotating, what it's made of, and how much gravity is pulling down on the surface of the star.
And doesn't knowing what the star is made of tell you all kinds of stuff about it as well? That can tell you maybe how old it is. That can tell you.
It doesn't tell you how old it is. It tells you what generation it is.
So how many populations of supernova, how much heavy metallic elements are in the star, and maybe how long, and so that, maybe how long it's been around. But I understand what you're saying. Yeah, and so, one of the analogies that I always like with this is that it's sort of like a polling station. Like up until this point, astronomers have done this work in a very manual process with the Parkus and with different instruments and different satellites and different observations, and gotten a real fraction of this number of stars, and that's told them sort of overall some things they know about the galaxy. And it's like you're watching the first polls come in on an election, and you're like, oh, it looks like my candidate is winning, but there's only a small number of polls that have actually reported in so far. But then over the course of the night, as all the polls come in, then you get a much better understanding. And so the assumptions that astronomers have made about the composition of the galaxy, about the motions, about what kinds of processes are going on in the galaxy, when you take it to this level, where 1% of the entire galaxy, it just tells you so much about, with a very high degree of accuracy, about what's going on here.
And getting at the how this is doing a survey, it goes beyond just the compositions to it. It's for the first time allowing us to sample periods of stellar evolution that are very brief, to allow us to get at an accurate stellar luminosity function. This is that distribution that tells us that for every one giant OB star, there are 500 little tiny red stars. I'm just making up numbers. We don't know the actual numbers. That's why we need this mission. And it also allows us to understand in our region of our galaxy what stars are on crazy orbits that are plunging through the disk versus, well, perhaps part of that cluster of stars that we formed with, or just other everyday disk stars. We're going to be able to get at that consensus of orbital mechanics, of compositions, of, well, baby stars to big stars, and everything in between. And most exciting to me is the fact that we are going to finally be able to examine, because we're going to have a large enough sample, the hard-to-observe rapid stages of stellar evolution.
Right, so we're going to see things like the T-Tauri stars and some of the Cepheid variables and some of the things that are in some of those final stages, red giants, younger hot stars, things like that.
And older stars in temporary phases, for instance, between when the hydrogen stops getting burned in the core of a star to when you get that flash of a shell burning. There's so many brief transitory phases as stars evolve, and we haven't well studied pretty much any of them.
If we're really lucky, maybe like a precursor to a supernova.
Yeah. I
That
mean,
would be
there's
amazing.
so many different things, and Gaia, the calibration phase for this mission took what felt like forever, but it's now mostly calibrated, and they've actually already detected their first supernova, and they're starting to get science results.
So we've talked a bit about the stars, and that really is the main goal of this mission is what they're going to be doing for the stars in the Milky Way. But because they're looking at bright stuff in all directions, there's just a pile of other science data that they're going to be gathering. So let's talk about a few of them.
So my favorite rogue science result I didn't know they were going to get until I started reading up on the mission is they're actually going to be able to get more accurate measurements of how the sun gravitationally bends the light of background stars as they compare looking over, under, beside the sun, pick a direction around the sun, and then looking at those same stars with the sun behind the spacecraft and seeing how the astrometry changes, whether or not you have gravity from the sun affecting the path of that light. This is going to be very precise confirmation of the theory of relativity, not that it needs more precise.
Will Einstein be right?
Yes, he will, but it's still cool. And the fact that they have to start taking that into account, I mean, what blew my mind is a lot of this ancillary science that they're getting, they have to get to fix their astrometry. One of the reasons that they have to do such high resolution, or it's actually low resolution, but one of the reasons they have to do the low resolution spectral photometry that they're doing is their positions are actually sensitive to if a star is more red or more blue, its centroid will be in a slightly different place due to chromatic aberration. So they need to get at the color distribution of the stars so they can correct for the chromatic aberration. So all of this work to get at the very precise color of the star is also getting at its position more accurately. Getting at the bending caused by the sun is getting at the position more accurately. And then along the way, they're going to actually just, as extra science that comes at trying to get at these precise positions, they're going to be able to see how massive nearby planets that are massive and nearby to the star being observed are actually able to sway the motion of those stars. And this will give us precise measurements of the inclinations of those orbits that we couldn't otherwise get.
Right. So when we observe planets right now, we get the transit method where the planets pass in front of the star, and we got the radial velocity method where a heavy planet is yanking its parent star back and forth, forwards and backwards towards us. But are you saying that we might get a chance to be able to see the wobble of those stars in the sky because of the planet, side to side?
Yes, the side-to-side, up-to-down motion. What people had looked so hard for in Barnard's star, which is one of the more nearby stars, it was hoped that if it had planets, we'd see it this way. Nope, not there, but this is a new telescope with new instrumentation that's capable of so much more than we've been able to do with previous space-based missions. And this is just work that you can't do from the ground because our atmosphere distorts the light just far too much.
But that's the holy grail. Because, I mean, people don't realize when we find all these planets that we're discovering, they are all total flukes that the planet happens to be passing through the disk of the star from our perspective. Or with the radial velocity method, that they're lined up enough that the star is being yanked back and forth. But that's, when you think about the number of possible configurations of stars and planets from our perspective, that's a tiny fraction of the actual number of planets. You know, what's it got to take? So
by looking just at stars with something like the HARPS spectrograph, which we'll be talking about, I believe, in the next episode, we're able to get at a lot of planets with a variety of different orientations, but what we can't get at is the planet that goes around and around its star completely in the plane of the sky. So this would be the perfect candidate for trying to image the orbit, because it never passes in front of its star. It never gets closer to its star than whatever it happens to be at its peristellar location. But what we can't do is find those with a Doppler shift. We can find it with astrometry. So we can finally start to find those with this awesome mission. And for all of those ones that we can find that have cattywampus orbits of some sort, by combining the Doppler shift from highly precise instruments like HARPS with the highly precise astrometry, we can now get at the inclination, so we can get the full three-dimensional solution for the orbits for the first time.
Yeah, and so we may, and this again is a prototype, but if this methodology seems successful, then you can imagine a future version that is just going after this way of trying to find planets. It's going to be stunning, and it's just a side benefit of the mission.
And what's really kind of weird to think about is this is a spacecraft that its name Gaia actually comes from back when they thought that it was going to be the global astrometric interferometer for astrophysics. It was originally planned as multiple telescopes were feeding their light together, doing interferometry to get the most precise locations possible. As it went through its design phases, as budgets became realized, this is a billion-dollar mission, it no longer stayed an interferometer. They kept the name Gaia, changing the capitalization since it was no longer an acronym. But there's a lot of room to expand what we do with the instrumentation to keep pushing this idea further out and finding systems where smaller planets are creating those observed perturbations.
Yeah, and so where are we now in the status? I know the mission launched about 1.5 years ago.
Last fall, Northern Hemisphere fall, it finished its calibrations. And now we're into the science mode. Like I said, its first supernova has been found, and we're all waiting with nervous energy to start getting those first astrometric results, hopefully of some awesome Cepheids that will allow us to know, hey, do we have this whole distance ladder thing calibrated vaguely correctly? What gets me at a fundamental level is this mission has the potential to expand or contract the entire universe in terms of the numbers we put down on pieces of paper by several percent, because we just don't have highly accurate measurements of the actual luminosity and distance of a Cepheid. And that's what the Key project used to calibrate distances to the nearest galaxies.
And the mission is planned for 5 years, but assuming there's enough gyros on board, it can go further than that.
We'll see. It's always a matter of what do the budgets allow, and with it out at the Lagrange point, you have to know ahead of time this sucker can't be fixed. But it's out there now, and it's doing awesome science.
But is it in a stable? It's the L2 Lagrange?
It's the L2. So this is the one that's on a line between the Sun, Earth-Moon system, and nothing.
Right. So it's not super stable the way, say, the Trojan ones are, like the L4 and the L5.
It's stable enough. Like I said, this is also where we're going to stick the James Webb Space Telescope, because it's where the sun doesn't shine, and it's just going to sit there doing awesome science.
Oh, this is so exciting. Cool. Well, of course, we'll be publishing lots of news about it as the science starts to roll out. But this is going to be one of those sleepers. Just, mark my words. It was sort of like Rosetta. Like, you remember, we knew Rosetta was going to be huge. And most people had no idea that this was all about to happen. So mark my words right now. Gaia. You're going to hear so much about Gaia.
If you want to marvel at a true feat of optical engineering, no telescope has really impressed me with its design in terms of the simplicity and grace of its optical bench as this one. It's a really sweet design. Super.
Cool. All right. Well, thanks, Pamela, and we'll continue our cool missions next week. What was it again?
The HARPS.
HARPS. Awesome. All right. We'll talk to you all next week.
Talk to you later.
Don't go anywhere. Don't go anywhere.
We're just saving.
Just saving. Dropbox is getting full again.
Okay.
365. Export my audio.
Okay, bringing the window with questions back to where I can see it.
Okay, I am uploading my audio.
I love the way Guido describes Germany. Soggy and lukewarm. It's soggy and lukewarm here, too.
Okay, so let's see here. Tatiana Valevska, this is your language that you can speak. Are we going to send probe satellites close enough to our sun about it? I mean,
the Solar Dynamic Orbiter is doing a pretty amazing job. It's in the Lagrange point that's between the Earth and the Sun, and they're getting 4K images that are kind of to die for.
They just oh, someone at my front door. they just wrapped up 100 million images. I'll be back in 1 second. Sorry.
Okay.
You keep going with questions.
Okay, so this is where I ad-lib. Yeah, the Solar Dynamic Orbiter, I don't know what more we could possibly want right now. It does amazing work, and we don't have enough scientists to process all the awesome science it's doing. Everyone's discussing weather. It's kind of funny. So Michael Jobin says, we have snow en route here in Minnesota, just inches on the ground, a contrast with when I had a shoveled pile 10 feet. Yeah, we got a dusting. Our weather is alternating between plus and minus 1 degree with moisture falling from the sky in various phase states. Yes, Bob, cattywampus is a technical term. And if it's not, it needs to be. So Cecil Morgan asks, will it detect red dwarfs and brown dwarfs well enough to get an accurate population percentage of these types of stars? Yes. That's one of the amazing things. It's going to finally allow us to get at that dim end of the stellar luminosity function.
Yeah, I was actually gonna mention that, and then I forgot to mention it. But this, it's going to be looking for the bright stars because that's what you can see. And so, nearby, we're going to get the dimmer stars, but out further and further out. When you get the billion stars, the 1% of the entire Milky Way, you're really getting the bright ones because that's what you can see so far away. But it's going to get some of the dimmer ones as in closer, right?
Right. So the way to think about this is a telescope designed to try and get a stellar census out to several kiloparsecs. And while it won't be seeing the most faint, the lowest luminosity stars out to those distances, it will be picking them up at the less than a kiloparsec distances. So we will be within that several hundred to 1,000 parsec distance getting all of these faint little red dwarfs, and with the nearer distances, the brown dwarfs. Hipparchus was one of the ones that first started to give us a nearby census of the brown dwarfs. This one's going to start pushing that out further. Once we get a large enough bubble, then we can say, yes, now we know what the stellar luminosity function is.
I love this. Where'd it go? Oh, moved. I lost the darn. Okay, so anyway, the gist is put it in the L2. That's another way for, that's a scientific way of saying put it where. Oh, here we go. L2. This is from Ben Gaisley. L2 gives new meaning to the phrase "put it where the sun don't shine."
It's true. It's true.
Yeah.
I
Yeah.
struggle with. I mean, that's literally what we're doing with the James Webb Space Telescope. We're spending several $billion to stick a telescope where the sun don't shine.
Yeah. Okay. Let me see what else we got. So, I don't know, did you answer the question from Sylvan Westby about does the acronym Gaia relate to the mythological Gaia, Mother Earth and Mother of the Titans?
I think, and he goes on to say, to titanic amounts of data.
Yeah.
I think it's more titanic amounts of data reduction. The maths that are going to go into trying to process all the data, they're not even going to try and do any of the processing on the spacecraft. They're doing all of that down here on the ground. Gaia, I think, was originally a nice, friendly, forced acronym. It got kept for continuity because people were already calling it Gaia, and Gaia is Greek, so sure, why not? And yeah, then it's a happy coincidence of, wow, there's going to be a lot of data reduction required.
Sev Despotty asks, is Gaia cooled, and does it have a consumable fuel?
I don't know the answer to that. It's just straight out CCDs. It's not going very far into the infrared, so it should be fine. It's when you start getting into the infrared that you can no longer use thermoionic cooling.
But if it's in the Earth's shadow, how is it generating power?
It's got batteries on board.
So
it does actually. I'm seeing pictures with, yeah, that's just mirrors.
Yeah. Let's see where its power is. It uses 1900 watts.
Okay, let me look at a difference.
Uses the Lysa-Juice orbit that avoids blockage of the sun by the Earth, which would limit the amount of solar energy the satellite can produce with solar panels. So
okay, so it does have solar panels that just aren't in the diagram I'm looking at.
it has a 10-meter sunshade. The
okay.
always faces the sun, and that cools the equipment.
Okay.
So it actually isn't put where the sun doesn't shine.
It's orbiting where the sun doesn't shine.
Orbiting where the sun doesn't shine, but it is in sunlight. What's nice is that it's away from the it's in a nice stable place where we can communicate with it on a regular basis. It sits in a very specific spot in the sky. And yeah. This is a good question. So Will 1311 asks, will we get any observational data that will help us understand dark matter? And I haven't seen any questions of that. Right. I guess the question is there dark matter in the galaxy? And if so, would the Gaia spacecraft be able to see it maybe through gravitational microlensing?
No, because the measurements it's making aren't the right type to do that. Yes, there is dark matter in the galaxy. That's a given. But what it's doing in calculating its orbit is it's looking at, or it's not looking at, it allows you to get at what is the total mass inside the orbit of this star, the total mass inside the orbit of that star. And orbits don't care if it's baryonic or non-baryonic matter.
So here's what the Google says. By watching for the large-scale motion of stars in our galaxy, it will also probe the distribution of dark matter, the invisible substance thought to hold our galaxy together. So yes.
I don't fully agree with the Googles there.
Well, this is on the ESA site.
Okay.
So
I don't know how that would work. I'll have to go read the papers. Okay.
Yeah. So something about watching the way the stars are moved as they move through the galaxy may help us understand a bit more about the distribution of the dark matter within the galaxy.
That assumes a complete census of all luminous matter.
Well, more like you watch the motion of a star and you can't account for its motion in any way other than it's being held in place or being attracted by dark matter, right?
That still assumes a complete distribution of luminous matter that's understood.
Right, because otherwise it would just be stars, right?
Yeah. Well, and gas is still normal matter and dust is baryonic matter. So there's no way looking at this to differentiate between something getting pulled around by a non-luminous cloud of hydrogen versus a cloud of non-baryonic dark matter.
Yeah. These are all, again, these are all just side benefits. Like, oh, and by the way, we also mapped out the dark matter in the Milky Way. And now we know what it is, because we're Gaia and we're the best. So, again, mark my words. Mark them! This is going to be one of the most important space missions that have been launched in a very long time. Let me check the comments on the event page.
I'm not seeing anything.
A lot of people talking about snow.
I want snow. Can I have some of the snow, Boston people? You have more than enough.
Are you crazy?
I like snow, and we haven't gotten any that stayed this year.
That's crazy. All right. Let me see if I have any questions that people have emailed me now.
I just want 5 inches, a good 5 inches of snow. One good solid snowstorm.
I'm all out of questions.
Okay.
I could probably dig deeper, but I don't know if there's anything on... Nope, I got nothing else. So if anyone's got any more questions, now is your chance. And if not, I think we can wrap this up. And so just to give people then advance notice, what's the mission that we're going to be talking about next week, the HARPS? What's the gist of that? It's not a mission.
It's an interferometer on a ground-based telescope.
Okay.
It gets used to very precisely measure the Doppler shifts of stars, and it's what is used to confirm a lot of the stuff that's coming down from the various transit observations.
You got the question from Cecil Morgan, right? About astroseismology. Yeah, I missed that part. Okay. Well, I think we can wrap this up then.
Okay.
So, wait. One last question. So Will1311 says, thanks for my answer. My second question is whether there are any relativistic ideas out there. Oh, the stupid Q&A app. Relativistic ideas out there for observing the opposite side of the galaxy or even the great attractor through the galactic core.
I'm not sure how that would work with the great attractor is a galaxy issue, and this is looking at stars. So I don't know if they're going to get anywhere near the needed resolution on the galaxy spectra, just because galaxies are so much fainter.
Right. So with the great attractor, yeah, you're seeing these galaxies move towards the great attractor through their various red shifts and blue shifts, but I don't think there's anything that Gaia is going to be able to do to see the stars that are blocked by the dust and gas at the center of the in the halo.
That requires infrared, and yeah, I different problem for a different telescope.
Yeah. It is pretty amazing how far with the infrared telescopes they've been able to push their mapping out the other side of the Milky Way, just in the way that they've been able to map out the other side of the sun. That's just astonishing that they can do that. So, they can actually see they can see what's going on the opposite side of the sun through its ripples.
Yeah.
It's amazing. So the astronomers are clever. They'll figure this kind of thing out. Okay, cool. Well, let's wrap things up. So thanks again, Pamela. Thanks, everyone, for asking all your questions. And we will see all of you next week.
Sounds good, Fraser. I'll talk to you later.